Is it that after this period, in period 2 you have mathematics? You don't have mathematics. Other period 2. But in period 2 I have a lesson in Form 4. If you want to go to there, it's also fine because I'm also just teaching as well. And then you can also refresh your memory. How about that? Is it okay? Can you see it clearly? If you cannot, just move forward. I don't know how to turn it brighter. I think it explains it. Now, so but what I want to do is just really to pretend that you learn nothing and then start from ground zero, and then we'll talk about one or two particular topics that you want me to go through. If you and just in case you don't have any topic you want me to go through in particular, then that's why I need to have a preferred list. So therefore, yesterday in the class chat, I asked if you have any topic you want me to go through, please let me know. But if you are here, then of course I will do the topics you want me to go through. That will be the case. Now, first of all, when you talk about book 2, maybe too small. Book 2. So book 2 will be about so-called forces. And to talk about forces, I think the first thing we need to talk about is about the motion first. So we have displacement, velocity, and acceleration. That we have the so-called free kinematics variables. So they are the displacement S, velocity V, and then acceleration. Now these three kinematic variables are important, and we first of all, although it seems very simple, but actually if you look at the past paper question for multiple choice in particular, is that they usually still reserve a few questions to test you if you really understand the meaning behind these three kinematic variables. In particular, one thing you need to be aware of is that they are all vectors. So therefore, they will have direction in it. In particular, if you are talking about a direction of one vector and then compared to another vector which is in the opposite direction, you need to represent it with a negative sign. For example, displacement. Let's say for a cliff like this, I throw a ball vertically upward, and then go up and then comes down, and then at this moment it's going down, and then it continue to go down afterwards. For example, for this kind of motion, then you have to have the idea that the velocity is positive at the very beginning, and then the velocity is negative after it comes back down. And then the negative velocity is expected at the end. Because the velocity is a vector, it has direction, so therefore it's necessary to put in the correct sign for the direction of vectors. Well, similarly, for displacement, we also need to be careful. For example, at this point here, the displacement is positive because it has displaced upward from the initial position, while however at this point the displacement is 0 because it goes up and it comes back down. So it's not, the distance is of course not 0 because it really has traveled a distance, but it has come back to its initial position in terms of a vectors, then that means it actually has 0 displacement. So therefore it has 0 displacement where it's just come back down at the same level. And then at the end, when it's fall to the bottom of the cliff, then the displacement will be negative because relative to the initial position, the position of the object is now below the initial position. So therefore, the displacement to be negative. So this is something that we have to be careful that the sign is really matters. And this is usually the things you need to be careful, because you are responsible to substitute the correct number. If you did not substitute the correct sign of the information, then you will not get the correct answer. The sign matters. Now, second is that when you talk about displacement, velocity, and acceleration, we will frequently sometimes come across the so-called the average value of it. So, for example, we can have some question that will ask, what is the average velocity? Then in this case, then we need to calculate the average velocity by total displacement over time taken. Well, one good example would be the circular motion. That in a circular motion, like a circle, like this, that when the object starts from here, and then continue to go, and then come back and end at the same point. At the same position. Then in this case, then although there is a distance, there's a total distance, but there's no total displacement, because its final position is at its initial position. So therefore, for example, in this case, although there is a motion, but because you're looking at the average value, so you need to look at the total displacement, but the total displacement is 0. So therefore, although there is a motion, but the average velocity is 0. So these are the two things that they want to talk about, even for these very basic kinematic variables. So after this, we have to look at the graphs, that if you're not looking at the average value, if you're looking at the instantaneous value, then we can talk about the graph S, V, and T. S, V, and A. Then we can look at the displacement time graph, velocity time graph, and acceleration time graph. We could only talk about the graph for the instantaneous value, because the graph is to tell you that at a certain time, what is the value of S, at a certain time, what is the value of V, what is the value of A. So the graphs, they are not average value. The graph is talking about instantaneous value. So when it comes to the graph, then after doing a few years of past paper, you will see that they always just ask about the relationship between these graphs. For example, if you want to start from the displacement time graph and you want to get information about velocity time graph, then you should look at the gradient. And if you start with the velocity time graph and then you want to get information about acceleration, then you also look at the gradient. In the sense that the reason behind is velocity is change in displacement over change in time. So accidentally, this just mathematically means the gradients of a graph, right? Delta y over delta x, the same form in mathematics. Similarly, the reason why we look at this as the gradient is because its acceleration equals to delta v over delta t. So mathematically, it is just saying that acceleration is the gradient of the VT graph. Well, conversely, if you start with acceleration time graph and you want to go back to study the velocity time graph, that means going from the right to the left, then you look at area. Although that is not technically correct, some textbook they may write, oh, I go from here to here, you look at the area. But actually it's not true, because area is just a number. You're not talking about, if you want to get a graph, you should have many, many numbers. So therefore, a better way to write this should be just this AT graph the area will give me information about change in velocity. And then the area of this velocity time graph will give us the change in displacement. So delta S and then the delta V. And then while the area of the displacement will have nothing, NA. It does not give me anything. So this is, I think, is a better way to represent the relationship between the three graphs. Anyhow, I think usually the most difficult part or the most important part, I think, for students to do it is they did not have the habit to look at the gradients or the area when they are given a graph. But this is actually a very important skill. You remember in Form 4, the first time I talk about this is, you just ask yourself why they need to give you a graph to a DSC student. The same graph can be seen or can be understood by primary school students. But what's the difference between you and a primary school student is that you have learned gradients and area. Right? You look at a straight line, they also know it's a straight line. But the primary school student, they will not understand gradients and area, but you do. So the reason you see graphs in exam is the examiner wants to test you whether you know how to use the gradients and area. So therefore, one very important habit or attitude will be look at the gradients and the area of a graph. They're usually giving you very important information, and that's usually where the answer is located. So for example here, this is the very first example that you can study the gradient and the area of the graph to get extra information. Okay, so this is the instantaneous value of the S, V, and A. Well, if you are not given a graph, but you're still looking at the instantaneous value of the displacement, velocity, and A, then that means you are studying kinematic equation. So you have the S equals to V plus U over 2 times T, S equals to UT plus half AT squared, V squared equals to U squared plus 2AS, and V equals to U plus AS, AT. So these four equations will be the equation relating the instantaneous value of the displacement, velocity, and acceleration, and does not involve any graph in it. And how to use this? Well, I think the logic is, there are so many variables where we can organize them or we can describe them because there will be always one variable missing for each equation, right? So for example, for the first equation, Donald, what is the equation, what is the variable missing? A. No A here. And then the second one? V. No V. And then no T. And then no S. So therefore, when, for example, when acceleration is not given in the question, and the question did not ask acceleration from you, so therefore acceleration is irrelevant. So therefore, we can use the first equation. This is irrelevant. Does not appear at all in my questions. Then that means there's no A in your question. Then we can use the first equation. Okay, so these are the variables that are missing. Then, but there is one thing that you need to be aware of is when we can use this equation. Now, of course, I have been saying that if you are talking about instantaneous value of the displacement, velocity, and acceleration, and you are not given a graph, then most probably you are using these four equations. But there is also some condition or assumption behind these four equations. What is the assumption? Kathy? This assumption is on acceleration. Under what kind of acceleration we can use these four equations? Constant acceleration. So when the acceleration is constant, then we can use these four equations. So I think I will put this as like an examination skills. Is that sometimes you may wonder why the teacher will know, oh, this question is about kinematic equation, while this question is not about kinematic equation, but it's about forces, it's about something else. Why we can tell that is because, first of all, I know when I look at the question, oh, it has constant acceleration. Then that means I can use these four equations. So therefore, this four equation is for constant acceleration. Well, what does that mean for constant acceleration? Well, we got example like I have a car, and then the car is accelerating or maybe decelerating at constant rate. For example, in this case, then this is the example we can use. Or the free fall, the one I float the ball on the upward and then go down the cliff. This is also constant acceleration, because in this case, the acceleration is only due to gravity. It's just minus 9.81. So therefore it's constant, therefore I can use these four kinematic equations for this kind of example that you throw the ball off the cliff. Or projectile motion. Projectile motion is also about the use of kinematic equation, because in this case we have ax is 0 and ay is equals to minus 9.81 and constant. Ax does not depend on time. At the beginning, ax is 0, and then when the ball is at the highest point, ax is also 0. When the ball is falling down, ax is also 0. At the beginning, ay is minus 9.81. When the ball is at the highest point, the acceleration ay is still minus 9.81. At the end, it's still minus 9.81. So it's constant, it does not change with time. That's why projectile motion is also a scenario that we can use these four equations. Then, what are the cases that we cannot use these four equations? That means, what are the examples that the acceleration is not constant? Can you think of one?
Air resistance.
Oh, with air resistance, good. With air resistance, and the air resistance is, of course, not a constant of time, because air resistance depends on velocity, and then the velocity changes over time. So therefore, you expect the air resistance is not constant. What else? This one cannot use. Think about one more.
Water resistance.
What?
Water resistance.
What is the same? The same. With resistance, I think with resistance, then you cannot use it.
Going up like a slope.
Yes, a slope. Or you can still use for inclined plane. So inclined plane, in this case, if you remember, the acceleration in the absence of friction is g sine theta. We may derive it later, but for inclined plane without friction, let me say one by one. So this is for the case which is smooth. If this is about the case that it has friction, then using forces we can derive it afterwards. Is that it will look at something like this. If there is a friction, minus F over M. Well, in this case, it's still okay. Although it's very complicated, g sine theta G sine theta minus F over M. However, they're still constant. So therefore, for inclined plane, even with friction, but with no air resistance, I can still use kinematic equations. But for slope with a curve, like this, or even like roller closure at the end, then the acceleration will not be constant. In this case, the acceleration is not constant, then you cannot use the kinematic equations. Okay, so this is that there's a changing. It cannot because it's a changing acceleration. Okay, so this is one thing that for examination skills you need to be aware of, is that when it's a constant acceleration, then you have the weapons of solving the problem using these 4 kinematic equations. There's also another one, and other skills that a teacher, when a teacher look at a question, I will say, oh, this must be a question on kinematic equation. There's also something missing. Mass, yes. Force, of course, there's no force here. But force usually is a variable, it's changing with time. So maybe it does not have to be there, but there's no mass. If you look at the book 2, or mechanics, or forces, you will immediately find out that I have to talk about mass once I start doing forces. When you draw free body diagram, you need to end it with F equals to ma. So if you don't have the mass, actually you can't solve the problem using free body diagram. You don't need to draw forces, because forces is only useful when you have mass. If you don't know the mass is, for example, just imagine, you know the same force. Let's say, I apply 10 Newton to an object. But 10 Newton cannot affect the motion of this. Maybe this is just a bottle of water. But maybe this is just a cell phone. 10 Newton on a cell phone and 10 Newton on a bottle of water is completely different. So you need to know the mass and the force to study the motion. So therefore, without mass, you don't need to worry about forces. Even you know the force, you know nothing. So therefore, when we call your memory of mechanics, at the very beginning we learned about this. We did not learn any forces. We did not need to use any mass. Conversely means if the question has no mass, the question did not talk about the value of the mass, then most likely we are dealing with kinematic equations. Because when you talk about mass, you will have so many different other weapons. You may have forces, momentum, energy. They use masses. But they did not give you mass, so you cannot talk about forces, you cannot talk about momentum, you cannot talk about moment, you cannot talk about energy. The only thing you're left with will be kinematic equations. So therefore, when you do the past paper afterwards, you may be aware of that. No mass is given. Okay, so this will be the things about displacement, velocity, and acceleration. You need to know the basic stuff, and then you need to know about the graph or graph analysis, and you need to use this equation here. There's a projectile motion about this part, but I think I don't jump into that part. I think projectile motion is a little bit more advanced. I think I will save it for later. But any question first for this? If no, then we can talk about forces. So the idea is basically I usually want to solve about displacement and velocity. That means I want to know where is the object, and I want to know how fast does it travels. So therefore, I want to find V, I want to find displacement. That means these three variables here, or these three variables here, actually I want to find these two. But in order for me to find these two, I need to know acceleration. So therefore, the question is, how do I find the value of acceleration? And that goes into forces. So forces that should be understood in this way. There are a few levels of understanding we have here. First of all, we have the Newton's law of motion. There are three of them. And then we have the first law. First law, it tells you that the resultant force is equal to 0, then you will have equilibrium. Equilibrium means that it is at rest or constant velocity. And the relationship here is actually twofold. It's two directions. If you know the resultant force is 0, then you know it's in equilibrium. Or if you know it is in equilibrium, you know that the resultant force should be 0. So therefore, the arrow here should be on both directions. So one very good example to illustrate this is also through multiple choice, is that they tells you that, yes. For example, in the textbook, they give you an example like this. There is like an arc here, and they put a textbook here, like this. And then we say that you can talk about the forces. You can have the weight going down. You can have a normal contact force on one side here, and then on the other side here. And then we say that, can this free body diagram be correct? Then we can use the Newton first law to say that. Because we know that this is at rest. Now maybe I say that it's at rest first. So the logic is, because I know it is at rest, therefore it must be in equilibrium. Therefore, from Newton's first law, it must have resultant force to be 0. But can the resultant force be 0 here? Then we go to the question like, I have 3 forces, how to find the resultant force? Well, the easy way is you just using head to tail to do it. So the resultant force can be found in many ways. It can be found by using head to tail. Method 1. Head to tail. Well, I have R2, and then, let's say, method 1, I have R2, and I have W going down, and I have R1 going up. So therefore, in this case, the resultant is actually from here to here. So therefore, the resultant force is actually to the right. That means not 0. Or you have the method 2. The method 2 is you do not use head to tail. You just resolve the forces. I have R2 to the right. I have R1 going up, and then I have W going down. So we realize that these two, they cancel. Therefore, the R2 is the only resultant force. So this is using components to solve it. And this is like using head to tail to solve it. But anyhow, in both methods, it tells you that the resultant force is not 0. So therefore, in this case, this free body diagram must be wrong. I need to have a force to balance the R2, which, well, I think about, can it be the weight? Cannot. Can it be another normal contact force? It cannot. Can it be the tension? It cannot. So finally will be friction. So it has to be a friction. So therefore, we need a leftward friction is needed. Okay. So this is the so-called Newton's first law, that we know the object or the system is at rest, and then therefore it implies us that mathematically we have the resultant force equal to 0, and then we use this equation to solve the questions. Well, after this, then we have the Newton's second law. The Newton's second law will be just very simple. It just tells you that F equals to ma, that the resultant force is equals to mass times acceleration. So this, again, to solve the resultant force, we have two methods to solve it. Either we use the component to solve it, or we use the head to tail to solve it. One example. An example will be that question that we saying that you have in a train, and then that train is, I don't know, it's accelerating, and then on the on the ceiling, there's a string connected to a mast, like this, and it is m, and this is theta. And we want to ask the acceleration. So therefore, let's say theta is equals to 10 degrees. Then I want to ask the acceleration of the train. Now, first of all, you know that we're talking about acceleration and you are given a mass. So it won't be the case of using kinematic equations. The reason they give you the mass is because they want you to solve this question using forces. And, okay, so what to do? Well, the first thing is we draw free body diagram. Every single time. I think this is again an examination skills. Every single time when you need to talk about forces, then draw free body diagram. And then we just need to brainstorm about the 4 forces we have: the weight, the tension, the normal contact force, and then the friction. This is like a beginner level because it's only one mass, and at advanced level you have 2 masses. But anyway, so we can draw the free body diagram. The free body diagram. In this case, I will have the tension, T. What else? Mg. Okay. Mg going down. Good. So after that, we need to find the resultant force. Well, there's 2 methods. Either you use head to tail or use the components. To me, most of the time, actually components would be more useful. So I will usually suggest students to use the component method first. The component method will be, I have to understand that there is a theta here. That means you got the same theta here. So I can erase this part. Then, to solve it using component, will be to identify that the T is not vertical nor horizontal. So we need to resolve the T to break it down into vertical and horizontal component. So therefore, we have the T some trigonometric function times theta, and then we have T and other trigonometric function times theta, and then mg going down. So after some analysis, you will see that the vertical component in this case should be cosine. And then the horizontal component should be sine. Okay. So therefore, this is how we solve it using component. And when we do this, then we can do the same thing as before. We can say we argue that these 2 are equal. So therefore, T cosine theta equals to mg. and then the remaining resultant force will be T sine theta. It's usually quite obvious after you do the components, after you resolve the components, it's usually quite clear which force is the resultant force. Most students, they are not able to get the final answer. From my point of view, is they did not attempt to draw the free body diagram. That will be quite sad, because if you did not have this attempt to draw the free body diagram, most likely you cannot really get the answer. 99% you cannot get the answer. So your first step is very important. Draw free body diagram. After you draw the free body diagram, then the second level will be whether you know when you have a free body diagram like this, you need to resolve components. Then once you know that you need to resolve component, then you are really close to the final answer. Because when you have this step here, I believe, even let's say I don't write down the equal sign here. I believe if I show this diagram to, let's say, Form 3 student, like half of them can already say that, these two cancel. And then the remaining one is there. Or intuitively. You just think about you're standing here, and then you get pulled by upward force and downward force and then rightward force, and then intuitively you already know you will experience the net effect to the right hand side. So therefore, once you draw free body diagram and resolve the component, you are very close to your final answer. So therefore, final answer will be, I got vertical forces balance each other. So therefore, d cosine theta mg, d cosine theta equals mg. And the resultant force is equals to the T sine theta. But we know that resultant force is ma. This is what Newton tells us. So therefore, these are the two equations that we obtain. But, okay, so this part will be, I would say, is like a standard force analysis that we expect students to know how to analyze the forces. And after this standard force analysis, we got these two equations. We got T cosine theta equals to mg, and we got T sine theta equals to ma. Then, back to the question. What is the acceleration of the train? Well, where is the acceleration of the train? You can find it here, ma. So therefore, technically, you can just say, what is A? A equals to T sine theta equals to m. But unfortunately, you're not given m and you're not given t. But never mind, you're not alone. You also have the second equation here. So therefore, when you do the past period question, then this go back to just some mathematics that what we can do is we divide one equation by the other. That we take T sine theta and then over T cosine theta. Let me put it here. I take T sine theta over T cosine theta. And then that means I'm taking MA over MG. This is quite a common skill, is that you just divide one equation by the other. In this way, most of the time, you can remove many unknown. Then, once you do this, then that means T is no longer there. You just have sine theta over cosine theta. And then also M is not there. You just have A over G. So therefore, your final answer will be A equals to G tangent theta. It turns out that the final answer is independent of M, independent of tangent. And therefore, they just need to tell you that, we got theta equals to 10 degrees, then you can already get the answer. So therefore, equals to 9.81 times tangent 10 degrees, and you get the answer. So you will see, wow, this is how much work we have to do. It is. There is really some work you have to do. There's the main dish is this part here, the standard analysis. Sooner or later, you will feel that actually, I don't care too much what they ask me. Because I found you will after a few practice, you will understand that no matter what they ask me here, let's say this time they ask me acceleration, or next time they ask me something else, or next time ask me theta, maybe. They give me an acceleration and I define theta, but never mind, I don't care what they ask me. I still need to go through this kind of standard analysis here. I still need to draw free body diagram, I still need to resolve component, and then I got two equations. And these two equations help me to solve whatever things they ask me to do. So this is a correct expectation. Yes, don't know.
The answer was like G tangent theta, right?
Yes.
But like if you draw a free body diagram of like instead of forces, acceleration, and you just like get the same thing but quicker.
In terms of forces, but we draw a diagram for acceleration.
Yeah, so like.
Okay, I know what you mean. For example, but you need to, let me draw the angle for you first. This is theta. Now, A is in this direction. G is in this direction. How can you know A is tangent? A is G tangent.
Up.
This one is up.
Yeah.
A, G.
Then he's still like technically G tangent A.
In this case would be, yes, you're right, yes. And you could, I know, how to say, you're right. For example, okay, I know G is going down and then A is going to the right, and then we can form a right angle triangle. And so that I know this is also theta. Therefore, the relationship between A and G should be tangent theta equals to A over G. Yes, you're right. But I just want to point out that this is correct only because when you draw this diagram, you're actually just doing the same thing as the weight is going down. You multiply M here, mg, and you multiply ma. And then you got this as a tension. Okay, and what you have done from this diagram will be obtained by a student who solve this question using head to tail. Because if let's say I'm using the method of head to tail, head to tail, I only have two forces here, T and mg. So when I say head to tail, I will say, head to tail like this. And then I realize that this will be the resultant force. But resultant force is nothing but ma. That means and then you just divide this right angle triangle by m, then you get this form.
Oh, so if I see a question like that, do I just use like the head to tail?
I will say, well, if you get the correct answer, of course it's okay, because you are actually using your physical intuition to solve this question. What intuition you're using here is, in fact, when you draw this, diagram, not everyone will draw it this way. Some student will say, oh, head to tail ma, so therefore this is T and this is mg. It's also fine. No one can say mg has to be this long. No one say that mg has to be just hit the bottom. Well, but if you have the correct physics intuition to say that, I know the resultant force must be pointing to the right. Therefore, I know the resultant force has to be here. So therefore, this mg cannot be too short. Because if the mg is too short, then it will violate my intuition. So therefore, I will say if you have the correct physics intuition, of course you can use the head to tail or you can use the component. But personally, I would suggest that if you to play safe, I would suggest you to use the component method. It will be better. Because when you draw, there is like so much degree of freedoms that you can draw shorter, longer, and then once you did not draw the correct free body diagram, then everything is wrong. But for the case of using component, it's only just sine and cosine. There's not much degree of freedom in it. As long as you did not make the mistake on the choice of sine and cosine, then you should able to reach the same equations, same set of equations like this, and then once you have this equation, you use this equation to solve. That's why but this is a good observation, I think. But I believe when you're working on a question, when let's say me, when I'm working on a question that I'm not familiar to, then I will first to use the component method first. Okay, so this is the an example of how to use the so-called F equal ma. So there's also a student that have a misconception. Newton physics is so easy, and then just F equal ma is so easy, but they actually have oversimplified things. So so-called when the physics teacher say F equals ma, it actually means this. The so-called F equals ma is only here. Here is F equal ma. The F equal ma just tells you these resultant force equals ma. But in order for you to apply this, actually you need to draw a free body diagram, and you need to decompose the forces. That's why we have to spend 2 chapters in this book to talk about forces. Okay, then after this, we have the Newton's third law. And Newton's third law, I think we can talk about that as well. The Newton's third law, which is, you can find a question, it's not very common, but in case if they really test you Newton's third law, it's actually a easy topic to solve as long as you have the correct concept or correct entry point. Not many question tests about Newton's third law, usually just multiple choice question. And then long question is also not very common. But anyway, we don't forget, or also which is include. What is Newton's third law? Is that for every action, we talk about the statement first. Although the statement is not very useful in terms of examination, but the statement is a statement. You need to know the statement. There is equal, for every action, there's an equal and opposite reaction. Action and reaction, they are just forces. So therefore you can say for every force, there is an equal and opposite force. And we call one of them is action, and another one is reaction. But actually, no one say that has to be action and that has to be reaction. They always come in pairs. So, but for examination purpose, I actually prefer you to understand it as when there is a force on B by A, on A by B, on A by B. A and B are two objects. Then there is an equal and opposite force on B by A. In my point of view, this is much easier to use. Instead, whenever you have a force, then you need to think about, okay, if I want to describe this force using force on A by B, then what is A, what is B? And once you write down on A by B, then you just swap the subject and the object. Then you get on B by A. So the very good many example that you can use. For example, let's say you have the box on another box. We call this box A, we call this box B. And then there's a friction between these two boxes. Then on A, let's say I'm pushing here. Then on A, there is a friction exerted on it. So there will be a force, a friction on A by B. On A, because this is on A now, on the free body diagram of A. So therefore, by action and reaction, by Newton's third law, then there must be, just think about it, therefore, there must be a friction on B by A. Well, therefore, there must be a force on B, and that there will be friction going in the opposite direction. Then to be on B by A. And then Newton's third law just tells you that these two forces must be of equal magnitude and opposite direction. There are many different examples. I could say A and B are not two bosses. You may say A is a student, B is the ground. When the student is walking, the student actually experiences a friction that pushing this student forward. That's why the student can walk forward. Well, how come? Is it because the student A is actually exerting a friction on the ground? You are pushing the ground backward, or you're pushing the floor backward when you are moving forward. So that means when you're walking, you let the ground to push you forward. But how can you have the ground push you forward? You need to push it backward. So the same thing on A by B, on B by A, on student by ground, on ground by student. Now, and this is the Newton's first law, second law, and the third law. I think this is the book to chapter 6. Chapter 6, yes. And then there's other forces as well, which is on chapter 7. But you could, today, if you want to do some practice immediately after listening to me, then you can go to your textbook, do the book 6. Yeah, book 6 will be about all this. Yeah. It will be very helpful. It's just all to clear your misconception on all the concepts. Oh, and I need to have another lesson. If you want to go to my Form 4 lesson, you can go to 514C. 514C. Should be enough seat. That should be enough seat.
Do magnetic fields and magnets next time?
Now?
No, next time.
Next time? Yeah. Next time, maybe I complete the chapter 7 first. Chapter 7 first. And then we can talk about magnetism.
What's chapter 7?
More about forces. Moments. A part of, yeah, actually I need to talk about a little bit on moments as well. Then it should be enough.